hold the screen until I say exclude. It's good.
It's good. Wait, can they hear me? Wait, which one? This one? Whoa. Yo. Yo. Oh, wait. Can they hear me? Okay. Yeah. Alright. Here is the second part of the 1081, what's it called? I don't know. The 1081, like, workshops, whatever. So, part 4, combinatorics. Wait, I can hear you, bro. Okay. So, we'll just start off with some whatchamacallit. We'll just start off with a bit of pigeonhole principle. It's like it kind of falls in combinatorics, it kind of falls in proofs and logic. It's like it's very combi flavor if you want to say. So like we might as well, so we just like put something here. So you have x1, y1 be distinct points of the Cartesian plane with integer coordinates, and you have to prove that at least one of the midpoints of the 2 points have integer coordinates. So like you note these choice words, right? You note the prove, and you note that it says prove at least one, and these are very choice words, and these are like really indicative of just a pigeonhole principle in general. So so like look at all of these. These are my homies. This is like Jamal. This is like Greg. You know, these are pigeons. Anyways, so yeah, so pigeonhole principle. So pigeonhole principle is that given there are n plus one pigeons, so across n pigeonholes, then at least one of the pigeonholes have two or more pigeons. And I feel like this is very like this is pretty obvious. It's very easy to understand. But there's the generalized pigeonhole principle, where you have n pigeons and k pigeonholes. There's at least one pigeonhole with n on k or more pigeons, where this is the ceiling function. So the ceiling function, basically it picks the integer that's equal or like the smallest integer that's greater or equal than the value. For example, the ceiling function of 2 is 2, but ceiling function of 2.1, this is equal to 3, and the ceiling function of pi is equal to 4. So for right now, we'll just have generalized pigeonhole principle. This thing will just be a given. It will just be an assumed fact for this course. Anyways, going back to the question, I don't feel the need to restate it. You can read it here if you want, and it'll be here in the next slide, anyways. So we note that the midpoint of the points A, B, and C, D is A plus C on 2 and B plus D on 2. And for the average of the two integers to be an integer, they must either be both even or be both odd. So in other words, what we can say is A and C and B and D must have the same parity. And parity just means like oddness or evenness of a number. So what does that mean? We've looked for all possible combinations of odd or even, or all combinations of parity of the coordinates. So we note that there's four different possibilities. It's odd, odd, even, and odd, even. But note that there will be 5 distinct points. So like by pigeonhole principle, 2 of those points will have the same parity on the integers. And since they have the same parity, we conclude that their midpoint will have integer coordinates as well. So are there any questions with this? All right, so that's just a little pigeonhole principle. Now on to combinatorics. So this is when you think of combinatorics, like these types of questions are usually what you think of. So here we have 2019 term 3 Q3 part I. So how many different ways are to distribute 80 identical balls and 40 distinct lollipops among 8 children? And there's 2 parts. Part A, we'll just look at part A for now, where part A is just with no further restrictions. We're just looking to do these things. We note, I think, like just before we go any further, we note some like very specific words that the balls are identical and the lollipops are distinct. Just remember this going forward. So like we note that this isn't although this is like kind of one problem, it's actually two problems. So we're looking to distribute our 80 identical balls among 8 children, and we're looking to distribute our 40 distinct lollipops among 8 children. So we can get the answer by multiplying these two, since like principle of multiplication, I believe it's called. So we'll look at this alpha. How do you distribute 80 identical balls among 8 distinct children? So there is a formula for this. It is going to, the general solution is n identical objects and r distinct boxes is n plus r minus 1, choose r minus 1. And if we substitute r, n, and r, since there are n balls, there's 80 balls and 8 children, we get 87 through 7. But like you can use a formula, you can do whatever, but there's the question, why does this formula work? So one way you could picture it is, instead of considering these as numbers, you could consider how would you consider? You could consider like you have your 80 balls in a line. So these are your balls, and we consider 7 barriers between them. So you have 80 balls and 70 barriers. And what the barriers do, they separate between like which child owns which. For example, if you place a barrier here, it means that your child 1 owns these 2 balls. And then if you say place a barrier here, it means your child 2 owns only this ball. So your barrier basically like, yeah, it separates it into regions, which like and like each child basically has a region assigned to them. So we note that if we have our 80 balls and we have our 8 children, if we have our 8 children, right, we want 8 distinct regions because each region we assign to a child. So how do we get 8 regions? We have 7 barriers. So in total, how many objects would there be? There's 80 balls, and then there's 7 barriers. And then we want to choose the placement of our 7 barriers amongst our 80 plus 7, which is 87 objects. So thus we get 80 through 7, as we've seen here below. So do people understand that, or should I go through it again, or like do I need to explain again? Is it fine? Okay. So now we move on to part beta, which is how do we distribute our 40 distinct lollipops among 8 children? So we note that the general solution for n distinct objects and r distinct boxes is r to n, and we substitute our 8 children, 40 lollipops. I'll just briefly go over why this works. This is a lot more intuitive than like the first one. So we note that with our first lollipop, we'll label our lollipops as lollipop 1, lollipop 2, ... lollipop 40. And we note that these lollipops are distinct. So our lollipop 1 has 8 choices to go to child 1, child 2, child 3, ... or child 8. So our lollipop 1 has 8 choices in which it can it has 8 children which it could be possessed by, and it has 8 choices. And similarly, lollipop 2 has lollipop 2 has 8 choices. And then and we note that like this argument works similarly for all the lollipops. So since lollipop 1, 8 choices, lollipop 2, 8 choices, since all of them have 8 choices, 40 lollipops, it'll just be 8 to the 40. So we get there's 8 to the 40 distinct, ways to distribute our 40 distinct lollipops among the 8 children. So are there any questions for that, or? Okay. So from our alpha, we got the value 87 through 7. from our beta, we got the value of 8 to the 40. So since since these two are independent of each other, we can just multiply them to find the amount of different ways to distribute the objects among the 8 children. So our final result is 8 to the 7, 87 choose 7 times 8 to the 40. So any questions there? Do you want me to repeat anything, or is it all good? Yeah, okay. So now let's move on to part B. Since part A was basically just looking at, how would we do this if there's no restrictions? How would we do this if it's like, quote unquote, clean in a sense? So part B, we're adding restrictions. We're like, it's kind of getting a bit messy. So how would we approach this? So, whatchamacallit? Now, the specific restrictions, however, each child gets at least 1 ball and exactly 5 lollipops. So, like before, we'll distribute it into 2 different problems, and then 2 different problems, alpha and beta, and we're looking to multiply our results in alpha and beta. So let's move on to part alpha. So how do we distribute 80 identical balls among 8 children, and each child must get at least 1 ball? So we can represent the amount of balls each child gets by xi, and then we get this equation, and we note that the general solution for n objects with artistic boxes is n-1 choose r-1, right? So we can, like before, we can just put in our values. We could get 79 choose 7, since n equals 80, r equals 8. But you're not really understanding why that's true. So I'll go over why this works. So we note that we have our n objects, and we have our boxes such that each each distinct box has at least 1. So what we could do, same thing again. We have our n identical objects. So in this case, it's n balls. So this is n balls. And we note that in between the balls, there's n-1 gaps in between the balls. So there's n-1 gaps. And we look to place our r-1 barriers in the n-1 gaps. So since there's n-1 gaps, r-1 barriers between them, we get n-1 choose r-1. And note that when we do it this way, it guarantees that each region will have a ball in between, because let's say we have a barrier here and barrier here. I'll make a different color so it's easier to see. So let's say if we have a barrier here and a barrier here, which is the closest they could be, we note that one ball is still in between them. So it's no matter what, when we split it, there will always be a ball between any 2 barriers. So that's basically the premise of why this why this general solution works. And like I said before, we just substitute in our values into the general solution, and we get 79 choose 7. So do you understand that, or do I need to go through it again? All right. So now we're moving on to part beta, which is we distribute our 40 distinct lollipops among the 8 children, such that each child gets exactly 5 lollipops. So how we do this? So what we can do is we can have our children in order pick the lollipops one by one. So we have our first child. Since they pick 5 lollipops, they can pick 5 lollipops out of the 40, which by definition is 40 choose 5, or this. And then after that, we have the second child pick from the remaining lollipops. And we note that since the first child already picked 5 lollipops, there will be 5 less lollipops to choose from. So we get 35 C5. And then we keep on doing that all the way until we get the last child, the 8th child, which has to choose 5 lollipops out of the remaining 5 lollipops. So thus, since each event is independent of each other, we can multiply them to get this many ways to give each child exactly 5 lollipops. What we can do further with this is we can just know we know the formula for n choose r is n factorial on n minus r factorial times r factorial. So we can just use this formula to simplify it even further. So we know this 40. So our first term's 4 factorial on 35 factorial times 5 factorial, and the next term is 35 factorial on 30 factorial times 5 factorial. So like et cetera, et cetera. So what we can do is we can basically cancel this, and we can cancel this with this. As you can see below here, we can cancel each term, like each term that isn't 5 factorial, and then and our final result will be 40 factorial on 5 factorial to the power of 8. So are there any questions there? Oh. Okay. And so from there, we note that the amount of ways to get each child at least 1 ball and exactly 5 lollipops is the product of our alpha and beta. So we know our alpha is 79 through 7, beta is 40 factorial on 5 factorial to the 8. So we note that there's 79 through 7 times 40 on 5 factorial to the 8 different ways to distribute the objects among your 8 children as desired. So any questions overall, like with part B, or? Yeah. So now let's move on to a different question. So like, I guess those restrictions, like, although they were restrictions, they were like kind of nice restrictions to deal with. We kind of already had like in place formula for them. But now we'll look into how we could like simplify something to give us lots, we look to simplify something into like a form which gives us a nice formula. So here's 2017, term 1, Q4, part 3. Consider the equation x1 plus x2 plus x3 all the way up to x6 is equal to 36, where all your xi's are non-negative integers. And how many solutions are there with all of the xi's being odd and xi's are less or equal to 7? So what we can do first, right, is we kind of want to remove some of the conditions, right? How could we simplify it being odd? So we know that every odd number, so if you have an odd number n, it's equal to 2m plus 1. So we look to express our xi's in terms of this. So instead of like n equals 2m plus 1, we make our x equals 2yi plus 1 for some integer yi. But so since we know that they're odd and they're non-negative, we note that our xi's are at least 1. So that means 2yi plus 1 is greater or equal to 1, or yi is greater or equal to 0. So, since we also have this upper bound, we can do a similar calculation, and we get our yi's are less or equal to 3. And we use this substitution, we do a bit of calculation, we get our yi sum to 15. So now we transformed our original condition into something that's a bit easier to work with. Now we don't have this odd thing, which is it's a bit annoying. So now we don't have it anymore, which is pretty nice. Now we consider the equation y, y2, y3, all the way up to y6, sum to 15, where all the yi's are non-negative integers. And then now we look for all solutions. We look for the number of solutions such that yi is less or equal to 3, right? So does everyone get that, or should I go through it again? Okay. So that was basically our first substitution. You can kind of consider it as a transformation, but like you can kind of frame it as a transformation, but like I'm pretty sure you're supposed to say it's a substitution. So now consider equation of y plus y2 all up to y6 is 15, and how many solutions such that yi is less or equal to 3. So we know that since yi is less or equal to 3, we can consider the substitution where yi is equal to 3 minus zi for non-negative integers zi. So what will this change the condition to? It will change it. 15 is equal to your 3 minus z1 plus 3 minus z2 all the way up, and you can just like you can collect the terms, and then you can just like do the calculations and get your z1 plus z2 all the way up to z6 is equal to 3, right? So now since our y1 since our yi's are greater than 0, we find that 3 minus zi is greater or equal to 0, and it means our zi's are less or equal to 3. But we note that this really isn't a restriction, because note that the sum of all zi's is already 3, so it can't exceed 3 either way. So like effectively we're only working with one condition, and that one condition is that your zi's are non-negative. So we already know the formula for this, right? So zi's are non-negative, and then they sum to some number. So this is stars and bars. So our 3, so in this case, our n is equal to 3, and then our r is equal to 6. So with n equals 3, r equals 6, we get the answer 3 plus 6 minus 1, choose 6 minus 1, which is 8, choose 5, which is 56 total solutions. So are there any questions? I feel like that might have been a bit fast. Are you sure? Yeah, okay. So this is how we would like simplify like some conditions to make it like nicer. It's like what you do for if you haven't done your lab test yet, this is like the premise for question 6C in your lab test 2 for 1081. And okay, so let's move towards like more quote unquote traditional counting. So we'll look at 2013, term 1, question 4, part 2. So we have S be the set of all 14 letter words from the 26 letters of English alphabet, where no letter is used more than once. So this condition is pretty important, where no letter is used more than once. So we'll look at part A first. How many such words are there altogether? So what we can do is we know we have 26 letters. No repetition is allowed because no letter is used more than once. Sorry. So since no repetition is allowed, and order of your letters does matter in the word, of course. Then we choose our 14 letters from 26 with ordering. So we know the formula for this. It's by definition 26p14 words altogether. So is that fine? Do people understand that? Oh, wait.
All right, just to quickly pick up from where that left off, just because of slight technical difficulties, we'll continue with this question. So, let us just consider, first off, how many such words are there? We figured out that with 26 letters, you're going to find all 14 words by using permutations, right? So, noting that repetition is not allowed, we are allowed to use permutations because we're considering elements and we're just picking them, okay? Picking them in any order, allowing for a permutation. And back to Juan.
Yeah, sorry, I had to take a phone call for a bit. Anyways, so we're back to the same premise. A set of all 14 letter words, 26 letters of the English alphabet. So question B is, how many words in S contain the subwords Julia or Tony? So this or here is very important. So how many subwords contain Julia or Tony? So note that what we can do is we can use inclusion-exclusion. So how inclusion-exclusion works, right, is basically the union of, if you consider, it's basically the union of two sets, the size of the union of two sets. It's the size of each set minus the middle. Because if you count this set here, we'll call this set A, and then you count how many elements are in this set B, you count each set of elements in A once, you count each set of elements in B once, but you note that you count the elements in A and B twice. So you have to subtract that at the end. So basically what inclusion exclusion is you're kind of like, you're basically just subtracting the double counting you're doing. So in this like simple case, it's going to be that A union B, the cardinality of A union B is equal to cardinality of A plus the cardinality of B minus the cardinality of A intersect B. So this is inclusion exclusion, and we use it for this question, right? So what we do is pick this. So what we do is we define the words containing Julia and Tony as A Julia, A Tony, as you can see. And to find the size of the union, we find the size of the sets A Julia, A Tony, and we subtract their intersection because these are much easier to calculate directly. So let's look at just finding. Okay, so here we'll just look to find what A Julia is. So to find the words with the subword Julia, we consider, so first things first, we want to select our letters. So if it contains the subword Julia, out of our 14 letters, we've already selected 5 here. So since we've selected 5, we note that there will be 9 letters left which we can select. So and note, since we already selected 5, there will only be 21 letters left to select from. So we note there are 21 C9 ways to choose these letters, right? So we've chosen our letters. What we do now, we consider the arrangements of the letters. So we want to arrange these, right? But we want to arrange these letters, but we want to keep the subword Julia intact. So what we can do is we consider Julia as one word. So we consider Julia we consider our objects as Julia and then our like other letters. So let's say like P, Q, ... right? So since there will be like 10 of these objects and we can orient them in any way, there will be 10 factorial different arrangements of our like quote unquote letters. So by multiplying these, we have 21 C9 ways to like choose our letters and 10 factorial ways to arrange them, which gives us 21 C9 times 10 factorial words which contain Julia. Is that clear, or would you like me to explain it a bit more? Oh, wait, excuse me? Because you have 9 letters here and the Julia. So that means there's like 10 objects, right? So do you have any other questions? Okay. So yeah. So anyways, just to reiterate, since there's 21C9 times 10 factorial words with Julia, the value of the magnitude of the cardinality of A Julia is equal to 21C9 times 10 factorial. So what we do next? We're looking to find A Tony. But this, like the way we find A Tony, it's practically identical to the way we've found the cardinality of A Julia. So just for completion, I'll just like go through it again. But it's basically, we already select our 4 letters, and so we have 10 letters we can select from. And since we selected 4 letters, there's 22 like letters left which we could select from, which gives us 22 C10 ways to choose the letters. And we know that since there's 10 letters and 1 Tony, there will be 11 objects, which we can arrange in 11 factorial different ways. So there's 11 factorial different arrangements. And thus, since there's like this many ways to choose the letters, there's this many ways to choose to arrange our letters. We find that there's like 22C10 times 11 factorial words which contain 20. So do people get that? Yeah, okay. And finally, we consider the cardinality of A Julia intersect A Tony. So we look for the words which contain both subwords Julia and Tony. So similar to above, we've already chosen 9 of the letters, so there's 5 letters here, which we could choose. And since we've chosen 9 letters, there's 17 letters left which we could choose from. So we get 17 choose 5 ways to choose the letters. And since we want to preserve both Julia and Tony, we consider both of them as like singular objects, along with the 5 remaining letters, which gives us 7 objects, and thus 7 factorial different arrangements. And thus we have 17 C5 times 7 factorial words with Julia and Tony. So this is the cardinality of this. So from inclusion-exclusion principle, which we kind of like described before, we have the union of A Julia and A Tony in terms of the cardinalities of these 3, which we calculated before, and thus the amount of words which contain either Julia or Tony is this value, which you can see on screen here. So are there any questions here? Yeah, okay. So now here's something like much simpler. So part C, how many words in S contain all 5 vowels? So we note that there's 5 vowels in the alphabet, as you know. So we select 5 vowels, right? So we already have A, E, I, O, U. But then there's 9 letters. There's 9 letters we are yet to choose. So how many ways are there to choose the 9 letters? There's 21 letters left. We want to choose 9 of them. So that's 21 C9 ways to choose the rest of the letters. And in terms of orientation, we don't care about like where these vowels are placed. We don't really care about the orientation as long as it just contains the vowels. So we just need to arrange the 14 letters. So that's just 14 factorial different arrangements. So hence there's 21 C9 times 14 factorial words in S with all 5 vowels. Is that clear? Okay. So now let's move on to a different question. 2012 T1 Q4 part 3. So here's the premise. We have 4 friends and they're playing hands of bridge. So you don't need to know what bridge is, just like a bit to clarify that. And so, but what happens is there's a standard pack of 52 playing cards, which is dealt, and each player gets 13 cards. So what we will look for here is we'll look to find the probability that June and Wayne together are dealt all 13 spades. So like out of the 26 cards that June and Wayne have, they have all 13 spades, right? So how do we find it? So how do we find the probability? It's the number of cases with the requirement on the total number of cases. So like the amount of ways to give June and Wayne 26 cards is 52 choose 26 because there's a total of 52 different cards. So I feel like this is pretty intuitive. So this is the total cases. Now to consider the number of cases with this requirement, what we do is we consider out of the 26 cards that June and Wayne possess together, 13 of them are already pre-selected. They're like fixed. They're the 13 spades. So that means there's like only 13 cards left which they can choose from. There's 13 cards left which they can get. And there's 39 remaining cards in the deck. So since you want to choose 13 cards, out of the 39 remaining cards, we get 39 C13, different ways they can have the suit of, there's 39 C13 ways they can be dealt all 13 spades. And thus the probability we'll get is just 39C13 divided by 52C26. Is that clear? Or, yeah, okay. So let's move on to part B. So here we'll look to find the probability that the cards Delta, June, and Wayne contain at least one complete suit. So not just like 13 spades, but it could be 13 spades, could be 13 hearts, could be 13 clubs, could be 13 diamonds, whatever. But I think something I'd like to note with our argument in part A, it's that it didn't really use that it had to be spades. Like this argument also works if it was hearts, if it was diamonds, if it was clubs. So like additionally from part A, we note that there's 52 C26 total cases. So we're kind of using so we're using this probability formula again with number of cases with requirement on total cases. So we know this is total cases. So now we'll look for the cases with the requirement. So what are we going to do? We're going to use inclusion-exclusion. So we note that to get any complete suit, any specific complete suit, there's 39 C13 different ways, right? And let's say we double up. Let's say we get 13 of like two different suits. For example, 13 spades and 13 hearts. There's only one way for this to happen, since that's going to be all your 26 cards, right? All your 26 cards will be pre-selected, and that works for any pair of suits out of the four. So, and also we note that since there's only 28 cards between them, they can't really get 3 or 4 different suits. So we use inclusion-exclusion principle again. So we find the way for them to get a complete suit is the ways for them to get spade, like specifically number of ways for them to get any complete suit is number of ways for them to get like a complete suit of spades plus the number of ways for them to get a complete suit of hearts or clubs or diamonds. But if we do it this way, we know that we double count every time they get two complete suits. So we have to subtract each time they get two complete suits. But we note that, like, for them to get two complete suits, there's only one possible way. So there's just going to be 4 choose 2 times 1 here. And then we note that the number of ways to get, like, a specific complete suit is 39C13. So our final value is going to be 4 times 39C13 minus 4C2. So are there any questions there, or are you sure? Okay. Yeah. So we note that from before, this is the total amount of ways, to get a complete suit, and we note that this is the total amount of 52C26 is the total amount of ways to get it's the total amount of like ways for them to get the 26 cards. So we note the probability is just this value here on 52C26 as desired. So yeah. So any questions here? Like, yeah. All right. So we're moving on to recursion here with 29T3Q3, part 3. So we consider the set of all n-digit numbers formed by the digits like 1 to 9. And we note that we let an be the number of such numbers containing an odd number of prime digits, and bn being a number of numbers containing an even number of prime digits. So part A is we write bn in terms of an, and we explain our answer. So I think something you note before is that because we note that each number either has an odd number of prime digits or an even number of prime digits. It's either or. You can't have both, you can't have none. So we note that our sum an plus bn must be the total number of n-digit numbers formed by the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9. So what is that value? We know that with each digit, there's 9 different possibilities which you can make that digit. So the amount of n-digit numbers just out of these 9 digits will just be 9 to the n, right? So thus we get that an plus bn is 9 to the n, or equivalently, bn is equal to 9 to the n minus an. So is that good? Do people understand it? All right. So we will be using this value, we'll be using this for part B, which is we look to obtain a recurrence relation for an, and we have to explain our answer. So, and also a important note, you don't need to solve the recurrence relation. So we note that an plus 1 plus bn equals 1 covers every n minus 1 digit number with no overlaps. So basically what we do here is we consider an n-digit number with an odd number of prime digits. So boom, 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 dot, 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 boom, and so there's n digits here. So what we can do, right, is we consider, okay, there's an odd amount of prime digits. Let's consider how many prime digits are in the first n minus 1 digits, right? So we have 2 cases. So our first case, which we describe here, let's say out of the first n minus 1 digits, so these first n minus 1 digits, there's an odd number of prime digits. So how many ways are there of this happening? There's, by definition, n minus 1 ways for odd first n minus 1 digits. But we note that if we want an odd number of prime digits, and our first n minus 1 digits have an odd number of prime digits, then our nth digit can't be prime, or else it will make it an even number of prime digits. So that means that our last digit here cannot be prime. And out of the digits from 1 to 9, we note that only 1, 4, 6, 8, and 9 are not prime. So we have 5 different choices. So we have 5 choices here. So thus, since we have 5 choices for the last digit and a minus 1 choices we have a minus 1 ways for the first n minus 1 digits to have an odd amount of primes. You in this specific case, you get 5 times n minus 1 ways to have n odd prime digits. So is this clear, or right? So this is our first value, 5 times n minus 1. So now we consider the other case. What if the first n minus 1 digits had an even number of prime digits? So boom, boom, dot, 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 boom, boom. So there's n minus 1 digits here, and we have the nth digit here. So how many ways are there of having an even number of prime digits in your first n minus 1 digits? By definition, that will be n minus 1 ways, right? And to make it make it in total an odd number of prime digits, you'd have to have this last digit prime. So what possible primes could we put there? We can only put 2, 3, 5, or 7. So there's 4 possibilities. So since there's 4 possibilities for our last digit, b n minus 1 ways for our first n minus 1 digits in this case, we get 4 times b n minus 1 ways in this specific case. So, yeah. Because those are the primes. We don't consider one a prime. Yeah, yeah, but like I think like prime is like two. It's whatchamacallit. Yeah, two divisors, but one only has one. But like it's really finicky. Just like in this instance, we'll say one is not prime. That's why we specified that one is not prime rather than saying one is composite earlier. So, anyways, so we say we have 4 times bn minus 1 ways in this case. We had 5 times an minus 1 ways in the first case. So we have an is equal to 5 times an minus 1 plus 4 times bn minus 1. And if you just use the substitution for part A, where we noted that 9 to the n, ooh, that was bad, where we noted that 9 to the n is equal to an plus bn, or equivalently bn is equal to 9 to the n minus an. We substitute this thing here, and then we can just simplify it, and we get our an in terms of an minus 1. So is that clear? Any questions? All right. So now let's move on to like, I would call these proper recurrence relations, but recurrence relations you have or will see in your lab 2 exams. So how we define a recurrence relation, we define it in the form of an plus c1 an minus 1 plus all the way up to ck a and k is equal to f of n, and f of n and ci are functions of n. So here's just like how we define it. It's linear if all of these ci's are constants. It's homogeneous if this is 0, and it's not homogeneous if it isn't. And yeah, so the solution for a linear homogeneous order 1, it's basically, what does it say? It says that an plus c1 an minus 1 is equal to 0, or your an is equal to minus c1 times, I'll just rub that out. So an is equal to minus c1 times an minus 1. And you can kind of see that your an, the formula for an is just going to be like your minus c1 to the power of n times some constant. Because like, you just like do it again, is equal to minus c1 squared times an minus 2 is equal to ... whatever. So you can kind of see why this is true. I won't dwell too much in it. You can like, I don't really think you need to know why it's even true for this course. You can just like kind of assume it's true, but it should be relatively intuitive. So I think this is something you should be more worried about, because like this does appear in your lab exams. So the solution to linear homogeneous order 2. So if you have the recurrence relation an plus p an minus 1 plus q an minus 2 is equal to 0, and if you consider your characteristic polynomial, which we basically transfer the coefficients of this recurrence relation into a polynomial, right? And if you let your solutions be alpha and beta, you can basically get that your an is equal to the nth power of your alpha plus your nth power of beta times some scalars. That's basically what it's saying here. If your alpha and beta are real and non-equal, then the general solution is this, where a and b are some constants. If they're real and equal, you want to like retain information in some sense, because if you just use this formula, you can kind of like lose out on a bit of information, because like you can increase your a by 1, you can decrease your b by 1, and it's still the same. So the way we would retain information is making this bn times b to the n, which like makes it distinct from your a times a to the n in some sense. And if alpha and beta are complex conjugates and they're equal to r times the exponent of plus minus theta, the general solution is just this. Yeah. And another thing I like to reiterate, like for this course, I think it's best to assume that this is just like given facts. Like the proof is pretty long, so yeah, just assume they're facts for now. So any questions here? Just like, yeah, okay. And okay, so with recurrential relations, I think this is pretty important. So how we want to solve non-homogeneous relations, so we split it into two. We have this solution, Hn, if it was homogeneous, and then we use the Pn to basically get rid, we kind of consider a Pn to get rid of like the non-homogeneity in some sense. So we kind of use Pn, like Pn gets rid of, so our Pn gets rid of f of n. So if you consider as like you want your Pn gets rid of f of n, like if your f of n is a constant, you want your Pn to be a constant to get rid of it. And if it's a polynomial, you want to get rid of it by having it the same polynomial. Same thing with exponential, same thing of product of previous. It's like, and the main way to get these is like, it's honestly just through guessing, and it's just through like being familiar with it. So it comes back to, if you do want to get like better at math, there is only one solution, and it's just to put in more work. There is no shortcut. So if you want to get better with recurrence relations, do more questions, get more familiar with it, basically. So here's 2019 T3 Q3 part 4. So we're just looking for the general solution to this recurrence relation. And it's just, it's going to get a bit ugly, but like I think just generally in math, you will have to have faith. You'll just have to have faith that you'll get there in the end. So we note that this is non-homogeneous, linear, and it's second order. It's non-homogeneous, it's linear, and it's second order. So what we do, first things first, we move this all to one side. Wait, was it originally on one side? No, never mind, I was already on one side. So what we do is we first solve the homogeneous, because like this is a lot easier to do. So the homogeneous is, let's say this wasn't here. Let's just say it wasn't there. So an minus 6 an minus 1 plus 9 an minus 2 is equal to 0. So we look at our characteristic polynomial, which is r squared minus 6r plus 9, because it's the same coefficients here. And we get the solutions are 3 and 3. And since the solutions are the same, we know that our Hn is in the form of a times 3 to the n plus bn times 3 to the n, since the solutions of the quadratic are the same. So now we know what our Hn is, we'll look for our Pn. So what our Pn does, as said before, we look to eliminate this part here. So since it's exponential, right? Since it's exponential, well, it's exponential and linear. So we're looking for Pn is a linear, and it's a linear times 3 to the n for some real numbers c and d, right? But like it only works if it doesn't share terms with our Hn, right? Because like then it would like interrupt our homogeneous solution in a sense. So we note that since our Cn is the same as the Bn here, we can't have this like as we can't like our original Pn like doesn't really work. So what we do, we multiply it by n. So if we multiply it by n, we get dn times 3 to the n plus cn squared times 3 to the n. Note that since this is cn squared, it's not really going to interfere with your bn anymore. But note that your dn now interferes with the bn. So you have to multiply by n again, right? So we use our Pn is equal to n squared times Cn plus d times 3 to the n. And to find the constants, we have to use our Pn in place of An. And then we know that this monstrosity here is equal to 5n times 3 to the n. And if we just do a little bit of calculations here, if we just like simplify it, we get 6cn minus 6c plus 2d is equal to 5n plus 0. So we compare the n terms. So we note this 6c is equal to this 5 here. So 6c equals 5. And we note that this minus 6c plus 2d is equal to 0 here. So 2d minus 6c equals 0. So if we solve this, we get the values c equals 5 on 6 and d equals 5 on 2. So our Pn is n squared times 5n on 6 plus 5 on 2 times 3 to the n. And if we add that to our Hn, we get the general solution here, which is An is equal to a times 3 to the n plus bn times 3 to the n plus n squared times 5n on 6 plus 5 on 2 times 3 to the n. So that was a bit convoluted. Like, do people have any questions? Like, is it fine? All right. So, yep, that's the end of combinatorics. I'll hand it over to Cyril for graphs. All right. Thank you.
Damn, that was hefty. Okay, let's look at some graph theory. Just a quick reminder, graph theory, graphs in this sense aren't like your x-axis, y-axis graphs. They're the graphs with vertices, these little circles here, and the lines between them. Just a quick reminder in case anybody forgot. Okay. That was a heavy breathe. Okay. So first we're going to look at the adjacency matrix. So the adjacency matrix of a graph describes the number of edges between the corresponding vertices. So let's say you have the vertices A, B, C, D, and they're labeled from like the first to the second to the third to the fourth. Then say, for example, this row here, this element here, the element on row 3, column 2, it has 2 edges, and it has the number 2. And what that represents in graph terms is that the number of edges going from vertex 3 to vertex 2 is 2. Okay? If you look at another element, say this one, it means that you can see that it's on row 2 and column 4. That means the number of edges going from vertex 2 to vertex 4 is 1. So there's only one edge going there. And if we look at one more element, say this one, it's on row 1, column 4. This means that the number of edges going from vertex 1 to vertex 4 is 0. They're disconnected. And this isn't the complete graph. You can look at the other numbers and you can try and construct what it is if you feel. Cool. So there we go. There's our definition. We got that little bracket notation over there. So with like the A, I, J, and the first I represents the row it's in, and the second I represents the column it's in. So yeah, nice algebraic labeling. Okay, part A of the question asks, does the graph contain any loops? If so, which vertices have loops incident to them? And a loop in this definition is an edge from vertex to itself. Okay, so if we have a vertex, if we have an edge from, say, a vertex A to itself, right, we can see that's an edge going from A to A. So going from, say, the ith vertex to the ith vertex. What that would look like in our adjacency matrix, say over here, is when the row is equal to the column. So if we go down here, right, we can see those are the elements along the diagonal. Okay, so using the property that it's a loop is going from A to A, the row and the column must be the same, it's a diagonal. So in this case, we see that A and B have non-zero numbers. That means there are edges going from A to A and B to B, while C and D here and here have no edges to themselves. So just to clarify quickly, A we denote as like the first edge, the first vertex, B is the second vertex, C is the third vertex, D is the fourth vertex. So when you read it off the elements and you read off which row and column they're in, you only refer to like this table here, this table here. Cool. Any questions? Should be pretty clear. All right. Now we want to know what how many parallel edges there are, or rather, what parallel edges there are. So parallel edges are sets of edges which coincide to the same vertex. So what this means is that if we have a vertex A and a vertex B, a parallel edges are like pairs of vertices, or say some set of vertices going from A to B and A to B again. Okay? So you can see these two are parallel because they go from A and they both go to B. Cool. So to figure out which edges are parallel, or which sets of edges are parallel, we want to like make sure we look at like what the candidate vertices can be. So if we consider like some A and B, if we have an edge going from A to B and another edge going from A to B, in our adjacency matrix, that'll be a number bigger than 1, right? Denoting that there are more than one edge going from A to B. So we simply look at the numbers bigger than 1. We can see they're in the highlighted red. And if we read off again the row and the column, these are all the edges we get. So one other thing worth noting is that this graph is undirected. So if there's an edge going from A to B, there's also an edge going from B to A. As if to say, you can almost draw the graph as if there's no lines between them, or there's no arrow pointing in either direction. Feel free to say to only include like the non-reversed versions of these, but make sure you specify if you do that. So if you only include these edges over here and exclude the flipped ones, make sure to specify, maybe the graph is undirected. Cool.
How did we tell that it was not a directed graph?
Yeah, sure. So to show that it's not a directed graph, or rather, to show that it's an undirected graph, make sure to check that the matrix is symmetric. So you can see here that the same number of edges going from vertex 1 to column 3, the same number go from vertex 3 to column 1. And you can similarly see that here and here, and here and here. Perhaps it's a dangerous assumption to make, but because it's symmetric, because if you flip along the diagonal, the elements are the same, you can say it's undirected. Okay, cool. Any questions? Nice. Right. Find the number of walks of length 3 from vertex B to vertex C. So this is kind of where adjacency matrices shine. We have the property that if we exponentiate a matrix, right, we actually get the number of walks directly reading off it. So matrix M denotes the walks of length 1 from one vertex to another. If you do the matrix multiplication with itself, you will then get the number of walks from one vertex to another. So if you take, for example, M to the N, right, this denotes the number of, this is the grid, the adjacency matrix of the number of N length walks from one vertex to another. Okay, so here we see that M cubed contains the number of 3 length walks between vertices. So such a vertex, if you do the matrix exponentiation, as an example, if you like to multiply matrices like 1, 2, 2, 1, 1, 3, 1, 1, right? To get the element in the first row, first column, wait, I shouldn't label that as 0. To get the entry in the first row, first column, you multiply this row and this column together, right? Or you take the dot product. So that's 1 times 1 plus 2 times 1, right? If you wanted to get first row, second column, that's 1 times 3 plus 2 times 1, so that's 5. And then you keep doing that. So the 1 at row 2, column 1, multiply row 2 and column 1. That's 2 times 1 plus 1 times 1. And 2 times, and then for this last element, 2 times 3 plus 1 times 1, 6. So this is a matrix multiplication. 7, sorry, got to add the 1. So that was a quick, dirty example. Feel free to like revise matrix multiplication if you don't remember it. But here you can see this is our adjacency matrix. And if we want to know the number of walks from vertex B, which would be the second vertex, right? So we read off the second row, and to vertex C, which is the third column, right? You only need to read off that element there. And you can see there are 38 length 3 walks. Alternatively, I think most people would be doing this online. So you can just calculate this.
On a computer, with access.
Yeah, so on a computer, in a computer lab, with access to Maple, you can simply calculate m cubed. If you're doing this by hand, just like a little tip, you can notice that when you do the matrix multiplication between, say, m squared and m, you have some like 3 by 3 matrix, right? And if you only need to know the number of walks from one vertex to another, right? Say the left one is m squared and the right matrix is m, you can just multiply the row and the column that they go between. So say you want to know the number of length 3 walks from 2 to 1, right? From vertex 2 to vertex 1, you can simply take the dot product of this, and that'll give you your answer. And what that's basically doing is it's only computing one entry in the matrix, and you're skipping over the others. If you want it to be like even hyper optimized, you only need, for m squared, you only need to calculate these entries here. So little trick if you want to speed up, but not too important for people in this course. Cool. Any questions? Nice. Sick. All right. Let's go over a more complicated and hefty question. So we have this description of a vertex set here. So we have, let G, W, H. So W and H are integers greater than or equal to 2. Be some graph with the following vertex set. The vertex set is denoted as like pairs of integers, right? Where A is between 1 and W and B is between 1 and H. Okay? So in a sense, this is almost like a Cartesian product between, like, say, the sets 1, 2, up to W. Sorry, 2, let me fix that up. Yeah, 1, 2, up to W. Cartesian producted with 1, 2, up to H. Cool. So hopefully that setup is clear. So these are tuples of integers bounded by W and H. And then we also denote an edge set. So the edge, this is undirected, but the edge is, you can see it's undirected because they use set notation here. The edge set is between pairs of vertices, W1 and H1, right? Such that this property holds. The difference between W2 and W1 plus the difference between H2 and H1 is equal to 1. Okay, so a big part of this question is understanding what this looks like, because they used very, very abstract notation here. So note, we want to find like W2 minus W1 plus H2 minus H1, right? For vertices W1, H1, and W2, H2, okay? So these are the only connections in our graph, and we want this to be equal to 1. So note that W2 and W1, right, are integers. Why is that? Because here, right, W1, H1, right, that comes from our vertex set here. And the elements of each vertex in the vertex set are integers. Why is this important? Well, if W2 and W1 are the same, right, if W2 and equals W1, then W2 minus W1 is 0. Okay? Otherwise, we can have W2 and W1 be distance 1 apart, or distance 2 apart, or distance 3 apart, etc. and etc. Right? This is important because if we have W2 minus W1 greater than 1, so if W2 and W1 are more than 1 apart, okay, this means that this equation here can never hold. The reason is H2 minus H1 is non-negative, right? If we add 2 plus, I don't know, some number, right, that's non-negative, it can't be negative, this is always going to be bigger than 1, and that's bad. Okay? So the set of vertices that are connected are going to be such that W2 minus W1 equals 1, or H2 minus H1 equals 1. Okay? But it's going to be an exclusive OR. So the reason why this is true is the only cases, as we've said, the only cases where this equality can hold is when W2 minus W1 and H2 minus H1 are both less than or equal to 1. Okay? But if we look at each of those four cases, if we look at each of those four possible cases, if W2 minus W1 is 1 and the other H2 minus H1 is also 1, the sum is 2. If they're both 0, the sum is 0. And the only time this entire sum here can be 1 is when only one of them is 1, when exactly one of them is 1. So what this ends up being is like, if you try and like check out, say, the adjacent vertices to 1, 1, right? You can only step up by 1 from the row part. So you can only connect to 2, 1, okay? Or you're connected to when this number is 1 more. So you're connected to 1, 2. Okay? Similarly, you can imagine 1, 2 is only connected to if you step up by 1 or step down by 1, but we can't have 0. Or when you step up by 1, step down by 1. So say 2, 2. Or 1, 3. Okay? And if you continue on with this construction of the graph, you can actually see that it constructs a grid. So feel free to think about this more. I want to really go into depth with this because this is important, but feel free to think about this more if you want. It's going to be a grid graph. Our definition is going to be a grid graph. Cool. Any questions, by the way? Okay, cool. Now that we've set up all of this, let's go and solve some questions. Find all the values of W and H for which GWH has an Euler path or Euler circuit. So first, our definitions are important. An Euler path is a path which covers every edge exactly once. So this is a non-closed, by definition of it being a path. And an Euler circuit is a circuit, so it's closed, that covers each edge exactly once. So as an example, let me whip up a quick graph here. Yeah, sure. If I was to do okay, so this is funny, but if I was to try and make an Euler circuit along this graph, I would try and visit every edge like this and then come back to where I started, okay? But if I was to do an Euler path, I don't know why that got erased. If I was to try and do like an Euler path, right? Let me say I do something like this. Yeah, sure. If I was to do an Euler path, I might do something like this. Notice that I don't revisit the same node. It's non-closed, right? So it's by definition a path, okay? So that there was an Euler path because I didn't go back to the same node. And the previous one, where I went back to the same node and visit every edge, is an Euler circuit. Okay, cool. Hopefully all that makes sense, because in most questions you can throw out that entirely, but it's still good to know. Because the conditions for an Euler path and an Euler circuit are probably more important to understanding, more important to solving questions than actually knowing what they are. So an Euler path exists if and only if there are exactly two vertices with odd degrees. And an Euler circuit, I've said cycle here, but an Euler circuit exists if and only if there are no odd degree vertices. i.e. when all the vertices have even degree. Okay, so if we were to try and look at our graphs G, W, H, which have these properties of odd or even degree vertices, let's first consider 5, 3. Okay, notice there's actually 4 classes of vertices in terms of what their degrees are. Okay, you have these corner ones here, right? What degree do these corner vertices here have? So we have 4 of these corner vertices. You can see that they connect 1 down and 1 to the right. So they actually all have degree 2. Okay, so maybe I'll write that somewhere. So corner has degree 2. Okay, and then you have another type. You have the edges, the edge vertices. The edge vertices, this is a bit weird. I call them edge vertices, but I really mean they're like the outside vertices, right? They have degree 3. They connect either to the left or to the right and down, or if they're an edge vertex here, they have 1, 2, 3 edges coming out of them. So they have degree 3. And finally, you have the ones on the inside. You have the vertices on the inside. Let's say they're called like the internal vertices. They have degree 4. So you have 1, 2, 3, 4. They can go in any of the 4 directions. And there's only at most 4, which also means these are our only types of vertices. Notice the only one that has odd degree are the edge or outside vertices. So, coming back to the question, if we look at how many odd degree vertices there are, there's 1, 2, 3, 4, 5, 6, 7, 8. That's way more than 2, way more than 0. There is no Euler path, no Euler circuit. Okay, this is good. So I've labeled them here again. So corner vertices, degree 2, edge vertices, degree 3, and internal vertices, degree 4. So now we want to ask ourselves to solve the question, which ones have 2 edge vertices, which ones have 0 edge vertices. And you might start to see this, like if you try and expand that graph out in terms of the number of columns it has, or down in terms of the number of rows it has, you will notice like the number of edge vertices, the ones on the outside here, decrease. So you can imagine that the ones which do have 2 edge vertices or 0 edge vertices are relatively small. Let's look at 2, 3, G2, 3. As we can see, it only has 2 edge vertices. That means that it has an Euler path. Similarly, if you flip it, G3, 2 edge vertices, Euler path. Probably shouldn't have done that. And then finally, not finally, that's it. You'll notice this is actually it. Because if we try and create a smaller graph, G2, 2, this one has no edge vertices. So, nothing. That means it's an Euler circuit. It has an Euler circuit. And this is important because you can't create any smaller graphs. Recall that W and H have to both be greater than or equal to 2. This means that these are like the smallest graphs, and however you extend them up or down, you won't get any Euler circuits or Euler paths. Okay, cool. Hopefully that explanation made sense. Nice. Okay. Now, part B, for which values of W and H is WH bipartite? More definitions. A bipartite graph. It's kind of in the name. If you look at the blue. Look at the bi means 2. That means your vertex set, so a graph is bipartite if in your vertex set you can like split it into 2 sets of vertices, right? I'm questioning whether this is bipartite. So yeah, it is. Nice, I'm so smart. I have 2 sets of vertices, some of which are boxed, right? So I have the sets of vertices that are boxed. And I say I have these vertices here, which are crossed out. Okay? Now look at these 2 sets. None of the boxed vertices connect to themselves. Okay? And furthermore, none of the crossed vertices connect to themselves. That means that this graph is bipartite because I've divided it up into 2 sets, right? Like 2 sets that don't share common elements and they cover the entire graph such that there's no connections between them. Cool. And one way to see this is that another way to see if like something is a bipartite graph or not is by asking if it can be represented into this shape here, like where the vertices can be moved around and the edges can be jostled around, where it looks kind of like this. You can divide the vertices into these two sections, and you only have edges going from like vertices between sections. So you will see this is common for bipartite graphs, this representation. And so now we want to see if we can divide our GWH graph into a bipartite graph. And the best way to do this is just to like do it, right? Like just try and do it rather. So we're going to do this by like denoting them as red and blue. Feel free to use your favorite shapes. I do not mind. So we start anywhere, right? And note that it doesn't matter where you start. It doesn't matter which set you assign the first one to, right? Let's try and assign the corner. Okay, let's call this blue. This is important because its adjacent vertices cannot have the same color as it, right? By it having to be a bipartite graph. Okay, so I'm going to color those adjacent vertices red. All right, now what about the ones adjacent to that? They can't be red as well, can they? So I have to color all of them blue. And you might start to see what's happening when I'm coloring these vertices. I'm sort of having like a flooding action. Let's say I color these ones red, because these are the adjacent ones, they can't be blue. These guys here, they all have to be red, okay? And that means that the next set of vertices here have to be blue. And these ones have to be red. And finally, the bottom right vertex has to be blue. So notice this flooding action has created like a checkerboard pattern, right? By us trying to force a bipartite, assignment, we've created a checkerboard pattern where we can see this is clearly bipartite because none of the blue vertices connect to each other, none of the red vertices connect to each other. Cool, that's very cool. If we wanted to, so to say G53 is bipartite, if we can also see this is true for any GWH doing this flooding action by making it a checkerboard of any sense. We can also see this is true for GWH generally, and we can prove this rigorously. So actually, it's not even that bad. I don't even need to draw anything. To show this, you can see if you assign I plus j where I plus j, ij where I plus j is even to one vertex set, and I plus j being odd to the other vertex set, you will never have I plus j odd and I plus j odd connect to each other. And you will never have I plus j even and I plus j even connect to each other. So that's one way you can go from like a visual representation of this to a rigorous representation. Cool. And now next question is, hopefully no questions, right? Okay, cool. Next question is explain why G95 has no Hamiltonian circuit. This one's very tricky, but let's try and first let's define what a Hamiltonian circuit is. Hamiltonian circuit is a circuit, should be circuit, not path, I'll correct that. A Hamiltonian circuit is a circuit which, instead of visiting every edge, like an Euler circuit, it now visits every vertex exactly once, and then goes back to itself. So, I guess as an example for G95, you can try and like see this as like a snaking action. Like you're playing a game of snake and you don't want to loop on yourself, but you want to go back to exactly where you were. So maybe you have something like this and you're trying to visit every vertex. Okay, very cool. And then you like go like this. Okay, I went back to where I originally was. That's a circuit, but it's not Hamiltonian because I missed these three vertices. So you might try and play around with this a bit more. Like I might go, okay, let me play snake like this. I'm like squiggling along. Oh, bit of a curveball. And then I go up like that. That's a circuit, but oh, I've missed one vertex. Okay, interesting. I'm trying really hard to make a Hamiltonian circuit and it's not working out. I'm gonna like move around and I always miss a vertex or I don't end up back where I was. If you've seen this problem before, if you've drawn this out, you might know the solution to this, and it has to do with the previous question we used, which was that it's bipartite, that we can color it in a certain way. And one way you can see this, one way you can figure out the solution is if you try and like play around with this example and try and draw a Hamiltonian circuit, or at least draw a Hamiltonian path, you'll notice that the path, if it starts at a blue vertex, always ends at a blue vertex. And this is no coincidence. Every step in your graph, because it's bipartite, will result in a change in vertex color. Okay, so what that means is if we start at a red vertex, we will go to a blue vertex on the next step, no matter where we are. These are all blue. Okay, and this is important because there are a Hamiltonian circuit, because it visits every vertex once, and because a circuit looks kind of like this, right? Notice that the number of edges in a circuit is the same as the number of vertices in it. How many vertices are in this entire graph? Well, it's 9 by 5, 45. 45 vertices, 45 edges in our hypothetical Hamiltonian circuit. Now, what is the issue with this? The issue is that this number is odd. That means the number of color changes is odd, right? If you try and look at what an odd number of color changes looks like, if you start at red and then you go to blue, odd, you change the color. Even, you keep the same color. Odd, you change the color. Even, you stay the same color. Odd, you change the color, right? So a Hamiltonian circuit, the end of a Hamiltonian circuit must start at a different color than you were, okay? So now you're at a different color in your Hamiltonian circuit. But also in a Hamiltonian circuit, we claim we were at the same vertex we started off with. We end up at the same vertex we were on originally. But this must be the same color, right? We've reached a contradiction. So for the sake of contradiction, if we assume a Hamiltonian circuit exists, by its properties, it must end at a different vertex color. It must end at a different vertex because it must end at a vertex with a different color, but it ends at the vertex that we started off with. Contradiction, no Hamiltonian circuit can exist. Cool. Does that make sense? Okay. Any questions? This is a common argument. This is a fun, fun math problem. Like you might have seen it before, but it is cool to go over. Okay. Let's look at this one. What is the minimum number of edges that can be added to G42 to make sure it's to ensure it's non-planar? So a planar graph. First, we'll show what a planar graph is. A planar graph very simply means that if you have like a graph like this, right, you can always move the vertices and edges around, right, such that it tiles the plane and no edges cross each other. So let me do it for this example here. I'm going to keep this vertex here, this edge here the same. And like imagine me moving the vertices around and the edges around. But I'm going to move this edge over here. Okay, I'm going to scoot it all the way over here. So I'm going to like try and replicate the divot. So it looks something like this. And then you might have something like that. And then because I scooted this vertex all the way here, there. So these two graphs are the same in terms of the vertices and edges that connect them. One could say they're isomorphic, right? And you can see that it tiles it's on the plane and none of the edges cross, which means it's planar. Yep.
Are you allowed to draw these edges curved?
Yep, good question. No, you're not allowed to. Yes, you're allowed to curve the edges. Yes, the edges can be curved if you wish, like that. This might be useful in some certain constructions to make something planar, where you can't just have straight edges. Okay, and now another theorem. It is good to revise on all these definitions and theorems and results because they can be a lot to memorize. But we have Kuratowski's theorem, which basically says that a graph is planar if and only if, let me do that, if and only if it has a K5 or a K33 subgraph. So what are those? A K5 graph is a graph with 5 vertices where all of them are connected to each other. A complete graph of size 5. Let's see if I drew it. Nope, I didn't. So just to draw what that looks like, it's basically a pentagon-looking thing with all the edges connected to each other in a star fashion. That's what K5 looks like. Cool. K33 is the complete bipartite graph, and it looks like that. Okay, so it's that kind of shape. You might have recognized this from like the housing appliances problem, but yeah, that's what it looks like. It's a bipartite graph where you connect as many edges as possible, and there's 3, 3 on each side. That's what these 3, 3 here denote. Okay, cool. So we want to show that we want to add the minimum number of edges to make sure it's non-planar. So, i.e., to ensure like it doesn't have a K5 or a K33 subgraph. Let's try and so we want to make the graph so that like it either has K5 or has K33. Okay. So we're doing like the negation of this. So we're trying to force K5 or K33 to appear. Let's try to do this in the minimum number of edges, and let's first focus on K5. So we want to first take like a set of vertices which are like grouped to each other as much as possible. So we have to add the minimum number of edges to them. So here, if we try and like take any 5 nodes, right, which are close together, like these, notice that you, how many edges will you need? You will need 5 new edges to them. So to try and draw this out, let's give it a go. You have these 4 connected in a grid like this, and you have 1 sticking out here. Now, if you try to draw that pentagon star shape again, you see you need 1, 2, 3, 4, and 5. There, sneaky little edge there. So you need 5 new edges. That's fine, maybe. Let's try and look for another smaller number. All right, not it found. All right, let's keep going. Let's try and make a K33 graph appear, because this seems like the best we can do to make a K55 appear. And for that, again, we'll try and take like a dense cluster. This is a pretty dense cluster over here. Because we're looking for a bipartite subgraph, we're actually going to use the vertex color to help us out. So this must be the vertex coloring of this dense cluster. And we can see we actually only need to add 2 edges to this. So let's see. This red edge here is connected to all the blue edges, right? So it's fine. But this red edge here is only connected to these 2 and needs to be connected to 1 more blue edge, this one. Okay? And to finish it off to be a K33 bipartite graph, this red edge here needs to be connected to this blue edge. Bang. Now, as you can see, this is now a bipartite graph. Let's just look here. This is now a bipartite graph. You can sort of unravel the edges, so like K11, 2, 2, and 3, 1, and you can try and see like these are its connections so far. Right? And the connections you need to make, this is just a new perspective, but the connections you need to make this a complete K33 is that and that. So only 2 edges again. So this means that we have another construction, right, that only needs 2 edges to make it non-planar. And this is pretty good. These 6 nodes are the best kind. And this is pretty good because if you imagine, it would be really hard to add a single edge and make the entire graph have like a K5 or K33 subgraph. Again, this is the best we've gotten, like just through exhausting cases. Like you can imagine like wherever you add an edge, right, using the definition of planarity directly, if I try and add an edge to this node, to say like this node, I can always curve it around here, right? Or if I was to try and add an edge here and here, I can curve it around. Or if I was trying to add an internal edge, I just add a straight line there, or even curve it around. So this is pretty good. because it means we can clearly see, again, we can clearly see we can't just add one edge to make it non-planar, and we found a way to make add two edges and make it non-planar. Therefore, 2 must be the minimum. Right, cool. Any questions about that question? Nice. Okay. More ideas concerning planarity. This is a weird one. I believe it might have been covered in the lectures only slightly briefly, but this is a pretty cool result. So we have for a simple planar graph, again, definitions. Simple means no loops and no parallel edges. Anything else? No? Cool. And we have, for a simple planar graph, E is less than or equal to 3v minus 6. There is a nice way to see this. Actually, I'll introduce the other result. But we also have, furthermore, if G contains no circuits of length 3, E is less than or equal to 2v minus 4. These are actually two very cool results. One way, I'll quickly sketch the proof, but if you try and imagine a planar graph that tiles the 2D plane, right? Something like this, say. What you want to use is Euler's vertices face edge theorem, right? For one. And another thing you want to use is the fact that each edge is bounded by two faces. So again, this isn't a necessary exercise, just feel free to do it for fun. Each edge is bounded by two faces, and so it's double counted, and each face sort of has at least 3 edges around it. And this condition with circuits containing no length 3, it basically means that each face will have at least 4 edges around it. Yep.
Is this also on the outside of the graph face?
Yes. Thanks for asking. So the faces here, just to quickly reiterate, are this, but also the outside region here technically counts as a face. That's a bit weird. I'm not sure if Euler's vertices face edges theorem is covered in the course. Well, if it is, have a look at it. It's kind of cool. But you don't need to know the proof for this. You just sort of need to know these inequalities, because they tend to be very useful for disproving planarity. That is to say, if this inequality doesn't hold, then the graph is non-planar. Similarly, if you know the graph has no circuits of length 3, but this inequality does not hold, then the graph is also non-planar. Okay, cool. And now we are going to use a question that does not use this property at all. Edward believes that the two graphs, A left and B right below, are isomorphic, but he doesn't know how to prove this. Okay, cool. Help Edward show that the graphs are isomorphic by providing an isomorphic vertex mapping to them. So an isomorphic vertex mapping to them is a rigorous way of expressing the idea I explained before of moving vertices and moving edges. So essentially what that entails is it's a mapping from the vertex set of, say, A to the vertex set of B, right, such that the edges between them are preserved. Such that if there's an edge from A1, A2 in the edge set of A, then this means that this is if and only if there's an edge from the vertex mapping A1 to A2 in the edge set of B. Again, to say if there's an edge from A1 to A2, then under the mapping there's also an edge in the other graph. Cool. And isomorphic if you can find such a mapping. Okay, cool. So there we go. That's the definition. We want to look at a bunch of graph invariants. So graph invariants are things that hold true between graphs that are supposedly isomorphic. If any of these things aren't true, then we can immediately say, hey, that's bad. The graphs aren't isomorphic. But it's also weird because if all of these things aren't true, then we still might not be sure if they're isomorphic. This is more to say that if all of these things are true, then they still might not. They might still be isomorphic. So this is to say these graph invariants help us construct a isomorphic mapping between two graphs. So some of them, the two easy ones are like the number of vertices and number of edges. These don't help you out too much, but ones that do are the degrees for each of the vertices, right? And also the neighbors, in terms of if you have a vertex of degree 3, right, connecting to a vertex of degree 4, right, that is an important result. And it helps us reduce some cases about what a vertex mapping could be. So it like connects to 4 degree 4 vertices, like this. That is useful. As we will see in this question. Also bipartiteness. So if there are two bipartite graphs, like if one is bipartite, the other isn't, you know. We have a bunch more here. Feel free to refer to this list: connectedness, Euler circuits, Hamiltonian circuits, etc. Cool. So these are like anything that's like, anything that, exactly as it says, anything that doesn't rely on a visual representation, any like property inherent to the abstract construction of the graph. Okay. Let's look at these graphs again, and we're going to color them by their degrees. So we see we have 4 degree 4 vertices here, okay, 2 degree 3 vertices, and 2 degree 2 vertices, okay, and similarly on the right, okay. So we've got some hints that they might be isomorphic, and then we try and construct a vertex mapping. So we can see A1 can either be mapped to either of the degree 4 vertices, right, because vertex degrees must be preserved. So the vertex degree of A must be the same as phi of A if they're isomorphic. Hopefully that makes sense why. So A1 can map to B1, or A1 could map to B4. And similarly, A2 could be mapped to B1 or B4, right? Either could work, theoretically. And similarly with the degree 3 and degree 2 vertices. But we can now narrow down our results to determine exactly which one is true by looking at the vertex neighbors. Importantly, if we have a look at vertex A, right, I'm just going to talk in terms of colors, but vertex A1 connects to a blue, green, green, and red vertex. It connects to 1 blue vertex, 2 green vertices, and 1 red vertex, right? Now let's look at, say, B4. B4 connects to 2 red vertices. That's bad, because the vertex neighbors of each vertex must be preserved. If A1 mapped to B4, that's not going to work out because we have B4 connecting to 2 degree 3 vertices, while A1 only connects to 1 of them. So instead, A1 must map to B1, something like this. And you can see that's true, or you can see that's probably going to hold because B1 connects to 2 green vertices, 1 red and 1 blue. We can do a similar thing if A1 maps to B1, then A2 must map to B4, because that's the only remaining degree 4 vertex. And we can do the same thing for the green vertices. A3 must map to B2 and not B4, because A3 connects to 2 blue vertices, while B5, let me move up a bit, B5 only connects to 1 blue vertex, right? So instead, A3 maps to B2 and not B5. And similarly, A6 would map to B5, as we see on the next slide. And finally, for the red verteces, A4 must map to B3, because if it mapped to B6, you can see it connects to blue, blue, and red. So B6 connects to blue, blue, and red, and A4 connects to red. Let me see. And A4 connects to red, green, and blue. They're not the same degree vertex neighbors, so that's also bad. So these must be the connections, right? And finally, we fill out the rest based on what the other one must be. And finally, we have these are our vertex mappings under the presuming this is isomorphic. So this doesn't fully prove that A and B are isomorphic. What you'd need to check as well is that the edges again are preserved by the vertex mapping. But I guess if this is like a sort of numbers question where you just like put in the vertices where the vertex mapping holds, you can see this is true. But if you wanted to do this rigorously, make sure you check the edges are all preserved between the vertex mappings. Okay, cool. Any questions? Any live questions? No live questions. Okay. Next question. Florence has been trying to analyze the frequency of traffic, and Florence has constructed the weighted graph G below. All right. And we want to find the minimal spanning, we want to find the weight of the minimum spanning algorithm, what the minimum spanning tree generates from the algorithm. So now we're considering weighted graphs. This is slightly different to normal undirected graphs without weights. So weights, like they're just a number on an edge. It's not too bad. So something like this, you can see has weight 6, that's 9, whatever. Okay, so a minimum spanning tree is a tree which covers all the vertices and has the lowest total edge weight for all such trees. So the tree, a tree kind of looks like, let's see, a tree kind of looks like something which doesn't have any loops. So I could construct a tree like this, right? So a spanning tree looks something like this. So you can see all the vertices are covered by the tree. There are no loops in this thing. So like, as in there's no cycles. Like if I connected this edge, it would no longer be a tree because I'd get a cycle like this. And there's an algorithm for doing this. It's called Kruskal's algorithm for generating the minimum spanning tree. And it basically goes order all the edges in G by weight. Okay, so we take all the edges and we take the next smallest one, take the lowest weighted edge, and include it into our tree unless it forms a circuit, that cycle I was talking about earlier. Okay, and then keep on doing that until you get a full tree. And it's kind of cool this algorithm works, and you can just trust it works, and if you want, you can prove why it works if you want. So let's just go through this. So what does it say? It says that I go through all of the edge weights in order from smallest to highest. So the smallest edges here are 1 and 1. Doesn't matter which order I go through them in. I can choose any of them. And then the next edge weights, because there's no 1, 1 edges anymore, are 2. Also, if I'm making mistakes, please let me know. So 2 there. Let's see. Are there any 3s? Nope. There's no 3 edge weights. There's a 4 here. Are there any other 4s? Nope, no other 4s. And then let's see. I have a 5 here. Do I have any other 5s? Nope, no other 5s. Then I try the 6s. 6. Nope, no other 6s. Just kidding. Haha. And then I have some 7s. Okay, yeah. I have some 7s. Okay. So here's where it starts getting interesting. Is this 7 here an edge that you can include? No, because it'll form a cycle as such. Uh-oh, that's bad. So don't include that. So don't include this 7. I won't cross all of them out. But you can see if you keep on doing this, I might include this 7, don't include that, include this 7, and don't include that 7 over there. Okay, cool. Now I look at all the 8s. So don't include that 8 there. Don't include this 8 or this 8. And don't include this 8 either. Actually, you can see that we're actually done with this algorithm. I've been rambling like a fool. You can see that the tree generated covers all the vertices. So it's a spanning tree. Again, there are no cycles. And because we perform the algorithm correctly, hopefully, it is a minimum spanning tree. Cool. Any questions about that? Yes?
Would we continue going along with it or not if we ended up with 2 disconnected kind of graphs as we were going through that still covered all of those?
Is that possible?
Well, let's say that the IF edge that we colored in first with a weight of 1 had a
Yep.
weight of 10 instead, right?
Yep.
If at a weight of 10 would continue filling in the whole graph.
Yep.
But then you'd have the top
Oh, I
and the
see.
bottom separate. Yeah.
Okay. Yep, sure. So slight mistake, thanks for correcting. You not only do you have to make sure that all the vertices are covered, but you have to make sure the entire tree is in this entire one section of connectedness. So you can see kind of like that. If I was to like, this tree basically means I can go from any edge, sorry, from any vertex to any other vertex by going along the edges of it. So say I wanted to go from D to G, I just like follow along here. Yeah, like that. So yeah, just make sure that's the case. If you want a property, the number of edges in your tree must be one less than the number of vertices in the entire graph. Cool. Sure. Any questions about that? Oh, sick. Okay. One final algorithm. Find the shortest distance from vertex A to vertex Z. So what we covered was minimum spanning trees. And while this gives you the total total sum of weights given by any spanning tree, this does not give you the shortest distance from any vertex to another vertex. You can clearly see that with actually D to G over here. We can't just trace along the minimum spanning tree to get the shortest distance from D to G. If we try and exit it, immediately we pick up a 7. That's going to increase our distance greatly. The optimal distance is 2G directly. Instead, we're going to use a different algorithm called Dijkstra's algorithm. So, Dijkstra's algorithm says, first you have a sort of set of edges, vertices you've already seen. It forms like a sort of tree. Let's start with the starting vertex, A. So we want to go from A to Z. So we start with A in our set T, and then we choose the smallest edge, right? That goes from a vertex in T to a vertex not in T, right? So say that goes from a vertex A to a vertex V, and then I add V to T, and then I repeat. Okay, let's see how that goes. So there goes the algorithm again. So to clarify, this kind of, we want to add a V such that the path from A to V is shortest, not the edge weight is shortest. So if we wanted to look, we first start off at A, right? And we add the weights 7, 7, and 7 like that. Or you add the vertices D, E, and H, because they're of shortest weight 7, 7, 7, shortest path 7, 7, 7. Okay. Now you want to look over and you want to consider the next adjacent vertices. So we have C, F, H, and G, and also I. So let's see. We have a path length, a minimum path length of 7 right now. If we try and go up to along this edge, you can see we've already seen E. We don't include that. So instead, let's see, the next shortest path looks something like this 7, 7, and this 7, 7 here. Okay. Oh, no, that's wrong. So the next shortest path it looks like is this 7, 6 over here. Okay. So you can see that because all of the edges we've come out from so far are 7. And to add another edge, we must like take the smallest edge because they're all the same length. So this has length 13. Okay. And so we add F to our T, our set T. Now we look for the next shortest path. And now, because there are no like connected 6 edges, we have one here and we have one here. So these paths are shortest because this path is length 14 and this is what length 14 as well. Okay. There is also one other path of length 14 and it's a bit subtle, but it's this one over here. 7 plus 6 plus 1. That's 14. Okay. So we've again noticed that we've built up this sort of tree structure like this. It's a nice way to visualize Dijkstra's algorithm. And the minimum vertex, minimum distance we've seen so far is 14. Okay, let's keep going. So now we want a distance that is 15. So if we might be tempted to immediately go like this and pick this edge over here, but that has distance 16. Instead, we can see there's actually a path of distance 15 over here. If we go like this, right? So like this, 7 plus 1 is 15. And then if you were to like look through, all of the other paths must branch from like this top section of the tree over here. So like 7 plus 9 is 16, so that's not smaller. Well, that's 16. 7 plus 9, that's huge. And you can keep on doing this, but what you'll eventually find that the next shortest paths are going to be 7, 1, and 2 like this, or 7, 1, or 7 and then 9. But actually, right, when we get to the 7, 1, and 2, sorry, 7, 6, 1, 2, which has distance 16, right, we can stop. The reason is because we found the shortest path from A to Z. Okay, cool. If you wanted, you can continue to construct this sort of weird tree of Dijkstra's algorithm. The next shortest path would be that, and the next shortest path here, I have, my brain has died. Let's see, 14, 16, 18. Is it 18? I suspect it's this. Yeah, I have a good feeling it's that, because this is a 2. Okay, cool. So, yep.
Might it be helpful to add the cumulative distance to those points as you go along?
Yeah. So if you do want to mark the cumulative distances as you go along, so that could be helpful. So like if you add a 15 here, and then 7 plus 9, 16 here. So when you're implementing Dijkstra's algorithm, this is generally how it's done. I guess this varies person to person, and if you are forgetful of what the cumulative distances so far to the vertex are, this can help you out. But I do think it's also fine, but beware you are privy to more mistakes if you take the entire path, regenerate it again. So up to you, choose. That is a good suggestion. If you want to like mark that this distance here is 14 and the distance here is 13 and the distance here is 14, feel free to. Cool. So with that, I guess to answer the question, the shortest path from A to Z is 7 plus 6 plus 1 plus 2 equals 17. No, it's not. 16. Yes, okay. We're all feeling a little tired. Okay, 16. All right, cool. Any other questions? Okay, cool. Hopefully all of that made sense. Graph theory is pretty content heavy, so feel free to like go back to any sections or refer to the textbook or lectures if you need. But yeah, those are the important points to look over. Thank you everybody for coming to the MathSoc 1081 revision seminar. What? Good luck with your studies. Good luck with the exam. Remember, your results aren't everything. Have fun, do well, live healthy, and attend our camp. Yeah, okay. Well, that's a long scroll. Let's see. I can try really hard and fail. It's not working. I'm gonna exit full screen and try. Yeah, I'm really trying. What if you do... Anyway, there's a camp. There's a camp with what's it, DataSoc?
Yeah.
DataSoc. Murder mystery. It's pretty cool. I would highly recommend it. I don't have a big murder, but that's kind of fun. We also have some other revisions on us. So check out our socials. Check out our Discord. You can see them there. We have a bunch of other events. If you don't like these boring revision lectures, then you can attend those as well. You have nuked the entire... This is bad. And obviously, if you have any questions about 1081 or anything we've covered, just pop them into our MathSoc Discord chat. We'll be happy to help you out. Surely we play some chug chug.
There it is.
There we go. Yay.
All right. See you guys. Good luck. And that'll conclude this stream.